Hi guys, so we are almost halfway through the course. So today we will complete module 6, and okay, let's see how it goes. So I'll start with what is called as the Bode plots. So last time we plotted Nyquist, and that gave us lot of information. It gave us if we start with an open loop system which is unstable, can the closed loop system be stable? It also gave us accurately or with some good measures or some good quantification of the relative stability, and we defined two different terms called the gain margin, in a way how much the system gain can be increased before it reaches the verge of instability, and also the phase margin, how much phase can be added to the system before it reaches the verge of instability. We also saw a open loop system which was unstable, and then we had to actually decrease the gain to get back the system into a stable configuration. Okay, so what we will do today is to look at little easier way of doing this, right? So it's called the Bode plot, and it's also called the logarithmic plot. So I guess somewhere in circuits you might have encountered this. So it consists of two graphs. Again, we start with a sinusoidal transfer function. So I first plot the logarithm of the magnitude, and so this magnitude, it will be versus the frequency, and also the phase angle against the frequency. Okay, so some basic nomenclature or some basic notations we will define. So the standard way to represent this is in terms of log to the base 10 and multiplied by 20. Not really important of why this is 20 and why not a logarithm to the base n. Okay, we will not worry about that, right. So the advantage when I do this, and which will be fairly obvious in the next few minutes, is that multiplications of magnitudes can simply be converted to addition. So we will see how these things actually translate to just or plotting the frequency response in the logarithmic scale just translates to just plotting straight lines like y equal to mx plus c. And if I have two lines, I know how the addition of those two looks like, right. So there's kind of lot of simplification. Whereas if when I was doing a Nyquist plot, I had to be careful of a lot of things, right. It wasn't really clear what happens at omega equal to 0 sometimes. So there are poles on the imaginary axis, and then there's a bunch of things, right. There could be multiple intersections on the real line. How do I detect those? All those were fairly tricky, and then it required lots of computation by hand, which could sometimes go wrong, right. So we'll see an easier method of doing that. Okay, so what is the advantages of this? Again, that low frequency characteristics I can really see very well, right. And in most practical systems, low frequency characteristics are very important in terms of disturbances, right. Disturbances always occur at low frequencies, or their characteristic is always a low frequency characteristic. Experimental determination of a transfer function is simple. So if I just plot how the system gain and the phase changes, and in a way that I just give the system lots of signals of varying frequencies, of course sinusoidal signals, and I just see what the output is. So earlier I said that I will do this experimental determination of a transfer function as a part of this lecture, but I will do a slight detour, right. So I will do this when in the module where we discuss non-minimum phase systems, and it will be a little more appropriate over there, because so far we haven't really talked of the classification of minimum and non-minimum phase. I'll not even make the distinction of that, because what we do from now on, we will try to avoid that and keep that separately for an elaborate discussion a little later, right. So what we'll also see interestingly is that it is very easy to get the static error constants through the Bode plots, right, which was not very obvious in the Nyquist diagrams, right. And what we'll see that these are just fairly easy to plot than Nyquist diagrams. Okay, so I'll leave the screen for a while, and I'll just go to the blackboard to do some initial things, and then I'll come back to the screen again. Okay, so there's a reason I'm using the board, because I think I can draw a little more freely. I just wouldn't directly want to show you the MATLAB plots, because that may not be very obvious of what I am doing, right. Okay, so what would we do in Bode plots? Okay, so we are given a transfer function in the sinusoidal form g of j omega, and the standard procedure is to plot (20 log of the magnitude of j omega versus the frequency, right, and the frequency will be in a log scale, and we will see what is also the importance of doing this on a log scale. Okay, so this magnitude is usually in this term referred to as decibels. Of course, omega is in the standard things. Okay, now if I look at a transfer function, okay, so what are of a sinusoidal transfer function g of j omega? Okay, first thing, there will be a gain k, right? Then there could be integral or derivative factors. Integral factor would mean a pole at the origin given by j omega power minus 1, and a derivative factor would be a 0 at the origin, which would mean like plus omega. Okay, if I could write it respectively, it will be minus plus. Okay, minus for the integral, this for, and if there are multiple poles, it will just be j omega minus plus n. Okay. Then there are first order factors, again both for the pole and the 0, and they would look like this: 1 plus j omega t, and remember I want to write the transfer function always in the time constant form. It will be minus 1 for a pole and plus 1 for a 0. Okay, and then lastly I will have quadratic factors, and this quadratic factor represents complex poles. Okay, how would they look like? Let's pick 1 minus twice zeta s is j omega over omega n plus, okay, this will also be a plus, j omega over omega n square. Okay, this will also be minus or plus 1, depending on if the poles are complex, depending on if we are dealing with poles or if we are dealing with zeros. And okay, earlier we had, for ease of notation, defined omega over omega n as u, and we sometimes use this notation for u, or for omega equal to omega n. Okay, let's start with the basic of all these things. Let's say my transfer function just has the gain term k. Okay, so what will we usually do, right? We'll say I take 20 log of the magnitude. Okay, so 20 log of the magnitude, which is simply k. This will represent the magnitude curve. Okay, so if I would just plot it for increasing frequencies, so I would just see that it is a horizontal line for all frequencies, right? So this horizontal line of magnitude k for all frequencies, right? and the phase contribution phi will always be equal to 0. So, the imaginary part is 0. Okay. Another thing to just look at, so if I have k, so how will the plot of ten times k look like? The phase will still be 0. Okay, so let me just go 20 log 10 times k. So this is 20 log of 10 plus 20 log of k. Log of 10 is 1, right? So this would be just 20 plus 20 log k. Right, so I'll have a line somewhere here. So this is all in decibels, right? Similarly, I can have 20, 40. So it'll just be, again, we're just adding constants, right? So the plot becomes quite straightforward. And lastly, well, this is 20 log k is minus 20 log of 1 minus k, 1 over k. Okay. So this is the basic one, right? How do we plot the gain k? It's just a straight line, horizontal line, versus when plotted versus the frequency, constant for all frequencies. Not surprising, there is no frequency term here, there is no j omega term in the sinusoidal transfer function, and the phase angle is always 0. Okay, so let me take the integral factor. One over j omega. This was good for us because it helped in the steady state analysis, or it had, adding an integrator always helps in reducing the steady state error, as we saw. Okay, so how will the magnitude look like? So I'm just looking at 20 log 1 over j omega, right? So this is, if I expand this, it will be 20 log of 1 minus 20 log of omega. This guy is 0. So what is left is minus 20 log of omega. Okay. Okay. So in this thing, so what we will do is on the omega scale, how is the frequency defined? Right. So this is omega, and as you say, this is on a log scale, right? So it's essentially log of omega. So if I just plot it on the x1, x2, so this is x2 minus x1, so it will be like the units which we say sometimes 1 centimeter, 1 meter, 1 millimeter, and so on, right? So it's always drawn to a scale. So here we will not do frequency from 1, 2, 3, 4, 5, 6, but we'll do in something called decades. And I'll explain you what it is in decades. So the frequencies are in decades, and there's a good advantage of why we do in decades. Okay, so a decade is a band from omega 1, some frequency omega 1 till 10 times omega 1. Okay. Okay, now what does a unit change in not omega, We are looking at log omega mean. Again, if we draw in the standard xy plane, if we talk of distances and time, so 1 unit change would mean 1 second, 1 minute, that is what we write here, right? Time in seconds, distance in meters, and so on. So what does a unit change in log omega mean? Okay, a unit change in log omega. So if it is just by time, I will say, well, this is t1, t2, and then t2 minus t1 is 1 second, right? And if it is say some other thing, distance, right? x1, x2, if I say this is the velocity in meters per second, x2 minus x1 is say 1 meter per second, right? These are the units, right, which we learn in high school how to draw the graphs. Okay, now what does a unit change in log of omega here mean? Okay, so this is log of omega 2 minus log of omega 1 is 1, the unit change. Okay. Now this is also written as log of omega 2 over omega 1 is 1, which means that omega 2 is 10 times omega 1. Okay. So which also means that here if I say, well, this is T3, T4 and so on, the distance between T2 and T1, which is 1 second, is also the same between T4 and T3, right? All the graph is drawn to that scale. So here the distance omega equal to 1 to omega equal to 10 is the same as from say omega equal to 4 to omega equal to 40. Can do this, right? Log of 10 over 1, right? You will get you say log of 10. Here also log of 40 over 40, right? So this is log of 10 over 1 is 1, log of 40 over 4 is also 1, right? So the distance between 1 to 10 is the same as the distance between 4 to 40, 40 to 400, all in multiples of 10, 400 to 4000 also, right? Okay. Okay, now we will come back to this one, right? So we will be interested in measuring the frequencies in decade. So what is here is in decade. So the frequencies usually will be on the log to the base 10 as multiples of 10, 0.1, 1, 10, 10 power 1, 10 power 2 and so on, right? And the distance between omega 2 omega 1, this is unit distance, unit distance, unit distance, all measured in the log scale this way, right? And this is what we need to be careful of. This is the only important thing here. Now once we do this, everything now translates to just writing down equations of a straight line. Okay, so just say this is my y axis, magnitude of g of j omega. So I am plotting magnitude of g of j omega in decibels versus the horizontal line, versus the horizontal axis, that is log omega. And this you can see is of the form y equal to minus mx, right? Magnitude y x is log of omega. This is a straight line, right? So if I were to just plot this from, okay, I will not plot at omega equal to 0 because the log value is not defined, but any value slightly apart from 0 we could plot. Okay, so at omega is 0.1, the magnitude is minus 20 log of 0.1, this will be 20. Okay, similarly at omega equal to 1. So, this is again all in decibels. At omega equal to 1, the magnitude is minus 20 log of 1 is 0. Omega equal to 1 or say omega equal to 10, the magnitude is minus 20 log of 10. This would be plus 20, sorry, minus 20. And similarly, you could do for omega equal to 100 and so on. Okay, so when we compare with this guy, we say, well, we are interested in the slope. So, give me the slope, and I could plot y equal to mx, right? This is a minus m, so a negative slope. Okay, so here you say a unit change in y. So, what is m? Right, this is like 11th standard coordinate geometry, y2 minus y1, x2 minus x1, right? Unit change in y over unit change in x. Okay. So, here we will see, right, what is the unit change? Unit change here is from 0.1 to 1 decade, right, and then here I am measuring the y axis in decibels. Okay. So, let us try to plot this, right. Say, let me say this is my minus 40 decibel, this is minus 20, 0, okay, let me draw it slightly better, minus 40, minus 20, this is 0, this is plus 20. Okay. Now, from point at omega equal to 0.1, the magnitude is 20. Okay. So, I am here, and at omega equal to 1, the magnitude is 0 on this 0 dB line here. Okay. Now, at omega equal to 10, I am here, right, and so on. So, I just draw a line which looks like this. Okay. Now, what is the slope? Right. See how much the y axis changes from here till here. When I measure from frequency of 0.1 till 1, it changes 20 in the negative direction. Again 1 till 10, it goes from 0 to minus 20, again negative 20, right. So, this has a slope of minus 20. Minus 20 what? What is in the horizontal axis? From 0.1 to 1, or 1 to 10, or 10 to 100. Okay, there will be 10 power 2, 10 power 3. So, this falls at a rate of minus 20 per decade, minus 20 decibels per decade. Okay. So, this is how we will measure the slope here. Again, it is very similar to what is happening here, right. Y2 minus y1, that is 20 decibels, x2 minus x1, right, that is a decade, right. And the advantage of doing this is that, okay, I will have your 10 power 3, 10 power 4 and so on, right, and frequencies are usually from very low frequencies of 1 hertz till 10 power 3, 10 power 4. And if I were to plot that on a graph sheet in the market, I would need to plot a simple transfer function, a graph sheet as big as a football stadium, right, and I would not want to do that, right. What instead I do, I can just do it in a log scale, right. In the log scale, okay, my frequencies, well, from 0.1 till 10 power 4, 10 power 6, I can really get very big frequencies in a small, A4 size this much of paper, right, whereas I cannot do it on a normal graph sheet. That is another advantage why we do this in the log scale, right. Okay. So, the magnitude of this looks like this. It has a negative slope of minus 20 decibels per decade. Okay. What about the phase? Phi is what? I am just looking at the magnitude of this, sorry, the angle of this, minus j omega. So, the phase, the angle, or say the angle or phase of 1 over j omega, that is phi, is always minus 90 degrees. If I draw the phase here, and if I say this is my 0 degree line, the phase will always be constant. at minus 90 degrees. Okay. So, the integral factor will have a magnitude plot at minus 20 decibels per decade and a phase plot which is minus 90. Okay. Now, how will the derivative factor look like? Use a different color. So, the derivative factor this is j omega. Okay, then I just write down these steps again. So, 20 log, so I am not looking at 20 log 1 over j omega, but I am looking at 20 log j omega, which is simply 20 log of omega. Okay, is the magnitude, right? Okay, now how will the plot of this look like? Okay, let us say at omega equal to 0.1, I am looking at minus 20 log, so it will not be minus anymore, there is a plus here, this one, 0.1. So, this would be now plus 20. Okay, no, sorry, 20 log 0.1, 0.1 is minus 1, so this will be minus 20. Okay. Similarly, at omega equal to 1, the magnitude of 20 log 1 is 0. Omega equal to 10, the magnitude of 20 log 10 is, this becomes plus 20 and so on. Okay. Now, let us start plotting this. At omega equal to 0.1, I am at minus 20, and at omega equal to 1, this one, this line or this color, omega equal to 20, I am at 0. Sorry, omega equal to 1, I am at 0, omega equal to 10, I am at plus 20. Okay. So, this is the plot of j omega. The white line is a plot of 1 over j omega, right? Just the mirror image, which is not surprising. And of course, what is the phase of phase of j omega? The phi is always plus 90 degrees, right? So, I will be all the time here. This is the phase of j omega at plus 90, and the white guy is the phase of 1 over j omega at minus 90 all the time, right? Straightforward, right? You just need to remember something like this, and then that the slope, okay, so this slope of the purple guy is positive 20 decibels per decade, right? Because I go from here till here, I increase 20, again I increase 20 and so on. So, each decade my magnitude goes up by 20 decibels in a straight line. Why is it straight line? Because of this guy. Okay, something slightly strange. Okay. What if, okay, I'll erase this, I won't make it any more messy. Okay, what if this is 2? Okay, so I am looking at 20 log of 1 over j omega square. Okay. Now, this is minus 20 log of again j omega square, or minus 20 times 2 log of j omega, or say just omega if I just look at the magnitude. Okay. So, this 2 just comes and sits here, right. Therefore, how will the straight line look like? It will still be a straight line. What is its slope? Minus 20 times 2, that is minus 40, right. So, it will be something like this, minus 40 decibels per decade. Okay, and what will be the phase? Phase, well, this is phase of 1 over j omega is minus 90. I have another of the same guy. This will be minus 180 degrees, all in degrees. Okay, just straightforward. I will not really now draw this scale and what is this and all. That is kind of now easy to compute. Okay, what happens to this guy? 20 log j omega square. This is 20 times 2 log of omega, right? Look at this number now. So this will be something like this. 40 decibels per decade, and an angle phi of 90 plus 90 is 180 degrees. Okay. So now I can just say, well, generalize this to, here it should be 2, right, for this analysis. I can generalize this to n here and n here, right. So what will change here is minus 20 times n, right, here also plus 20 times n. So the slope would be minus 20 times n decibel per decade, and here it would be plus 20 times n decibel per decade, right. So the angle would be minus of n times 90 degrees, and the angle here would be plus n times 90 degrees. Okay, straightforward. Okay, a little exercise, right. So if I have a transfer function now of say 10 over j omega, how will this go like? Well, I am just looking at the magnitude 20 log, so this will be 20 log of 10 minus 20 log of j omega. So, it will just be shifted by this number, right. So, I will not draw this, right, you just like y equal to mx plus c kind of thing. So, the slope is still here, this is y on the horizontal axis, this is my c is the intercept, minus mx, well, plus c, right, very straightforward. Okay, one observation we could make here is that the plot, or at least the magnitude plot of the 0 is just a mirror image of the pole, right. Here it was going at minus 20 and plus 20, right. Okay, we will see if that still continues or not. Okay, we will see now not these things, but what was the third kind of thing? That kind of thing was first order factors. First order factors are like this, j omega t plus 1. Okay, now how will the magnitude look like? 20 log 1 over j omega t plus 1, right, the magnitude of this thing. So, what is the magnitude? Well, you can just get this 20 log, I will get this upstairs, that would just be square root of 1 plus omega square t square, right, all again in decibels. Okay, now it is a little more interesting. It is no longer like y equal to mx plus c kind of form, it is a little more complicated, but we will try to simplify this. Okay, let us first draw, this looks like, this is my omega, this is my magnitude of g of j omega in decibels, and somewhere here would be the phase, right, angles. Okay, so let us see what happens at low frequencies. Low frequencies would mean omega is very small. Okay, omega is very small. This term can be ignored a bit, and you can say that minus 20 log of this guy is approximately minus 20 log of 1 is 0. Okay. So, what can I say is that for low frequencies, okay, if this is my 0 dB line, then I will just be here, right. Okay, I will use a color chalk for this one here. Okay. Until what point? Okay, let us see. Okay, let us see when this changes at high frequencies. High frequencies, omega significantly large as compared to T. So, minus 20 log of square root of 1 plus omega square T square is minus 20 log of omega T. Okay. So, this 1 goes away, and then omega square T square, the square root will just be omega T. Okay. So, how does this look like? This is minus 20 log omega minus 20 log of T. Okay. So, let us see at one particular interesting number here would be at, okay, I will not write this, I will write this here, at omega equal to 1 over T. In this, the magnitude, right, so like 20 log, okay, so 20 log of this entire guy, 20 log omega T with a sign here. Minus 20 log of omega T would be minus 20 log of 1, and that will be 0. Okay. So, let us see at some point of time or some frequency, say somewhere here, which is omega is 1 by T, this guy goes to 0. Okay. And after that, well, I am just moving downwards at this frequency, minus 20 log omega. And how does the plot of this look like? Well, I know it looks like this, right. This is again at a slope of minus 20 decibels per decade. And this also, well, I can say where it just moves here, these two guys meet here, and this goes. So, well, I am just making some approximations here, and I am just starting at very low frequencies, and I say I am just at the 0 dB line. I keep on continuing, and at higher frequency range, I am just doing this, going down at minus 20 decibels per decade. And this is, you can say that the plot can be approximated by two lines, right. So, this is one asymptote, this is the second asymptote. And these two meet at this point. What is this point? Omega equal to 1 over T, and this omega equal to 1 over T is the corner frequency. Okay. Now, you can see that, again, to say that for frequencies for frequencies between 0 to omega to 1 over t, my plot is approximated by the 0 dB line. Again for omega 1 over t infinity, it is goes down at minus 20 decibels per decade. Okay. So, these are the two approximations we get. Okay. Now, what is the actual plot? The actual plot may have some errors, right. So, this may at this omega equal to 1 over t, it may not be 0, but something somewhere close to 0. So, we will see about what that is. Okay. So, now how does the actual plot look like? Okay, we will come to the phase a little later. We will see what let's finish settle this business for. So, the error is usually the actual minus the approximate. Okay. So, what is the actual? The actual is, well, I can write this, the square root can go here, this is minus 10 log 1 plus omega square t square. This is the actual thing. The approximate was what? 10 log of omega. Okay. So, the minus and the minus become plus, approximate also had the minus 10, right. Okay. So, what happens at omega equal to 1 over t? This becomes minus 10 log of 2, okay, this will be omega t here. Okay. So, from here, right, the higher frequency things. So, minus 10 log 2, this will be 0, this would be minus 3 decibels, okay, no per decade, right. So, at omega equal to 1 over t, I am just having a error of minus 3 decibels. So, I am somewhere here, okay, where this length is minus 3 dB. Okay. Now, similarly, I could ask myself what happens at other points. Okay. So, the same guy at omega equal to 1 over 2 t would look like, well, minus 10 log 1 plus 1 over 4 plus 10 log omega is 1 over 2 t 1 by 2. Okay. So, this you could compute to be minus 1 dB, right. So, omega is 1 over 2 t. So, if I just say this is 1 over t, somewhere here, let us say, okay, let us say somewhere here is 1 over 2 t. So, here the error is 1 dB. Similarly, I can compute for omega is 2 t, the error is again minus 1 dB right here. Right, so, this is, say, omega is 2 t. So, the actual plot would look something like this. If I just use this purple color, at the low frequency it will still start here, and at some point it will start diverge, go a little bit, and then you see go down and then meet this guy asymptotically, right.
Should this be 20 log omega t, the approximate?
Here? Oh yeah, okay. Okay, this should be 20 because square root disappears. So, again just recall the approximate thing, right, that was 20 log with a minus sign omega square t square 1 over 2, that is 20 log omega t. Okay, sorry about that, this will again be 20, right. Okay, thanks for pointing that out. Okay, just be, I am sorry about this, the approximate ones we will still have 20. This will go 10 because the square root just comes here. Okay, so this is the approximate plot, and the exact plot would look something like this. Okay, and you see that the maximum error is just at the corner frequencies. So if I were to just vaguely plot how the error changes with frequency, right? So let's say this is 1 over t, this is the 0 error, so this will be some plot like this, right? And these are okay. In this case, this is minus 3 dB. Okay. So what about the phase here? So you can keep doing this for omega equal to 3t and so on, and just compute the errors. That's again a straightforward procedure. Okay. So we'll now come back to the phase. The phase angle. Phase angle, well, this is computed as the inverse tan of omega t. Okay, first from here. So at phi and at omega equal to 0, we'll have phi equal to 0. Omega is 1 over t. I have phi is minus 45. Sorry, there will be a minus here. And as omega goes to infinity, the phase goes to minus 90 degrees. So if I were to just plot it here, so let's say this is the 0 degree line. See, somewhere here is minus 45, somewhere here is minus 90, right? So the plot would look something like this. At omega equal to 0, I am asymptotically here, omega equal to 45, omega equal to 1 over t, I am at 45, so the phase would look something like this. Okay. Again, for exact values, you could compute, substitute for omega and t and just check. Okay. Right. Okay. So these were first order factors of the form 1 over j omega t plus 1. 1 over j omega t plus 1. I could do this exactly in the same way for a 0 or first order factor j omega t plus 1 in the numerator. Okay, so nothing would change, just that this minus 20 will now become plus 20, everything will be the same, just that in this case phi would be 0, phi would be 45, phi would be 90 for these three cases, right. So this is plus 90, 45, then the plot would okay, I'll use another chalk, this one. No, something like this, and the magnitude plot will just be again the same, right. If I just draw the asymptotic magnitude plot using the same color, so I am assuming both have the same corner frequencies, it will just be like this, right. So it will have a plus 20 decibel per decade, and the exact plot would look something like this for computing the errors, right, this, and then it just asymptotes here. Okay, so it's a very straightforward computation. All these pluses would go to minuses would go to plus and so on, and the way you compute for low frequencies, it will still be exactly the same. For higher frequencies, the approximation would still be the same, right. For low frequencies, I can just get rid of I can just get rid of this term. For higher frequencies, I can just get rid of this term, and it will just be like a mirror image, right. Similarly, even for this guy, right? It goes down, this guy. Okay, I'll pause here for a while, and then we'll continue to look at these guys, quadratic factors. This is a little interesting, right, to plot the errors. Okay, so we deal with these quadratic factors. So let's say they are of the form 1 over, this is my g of j omega is 1 over 1 plus 2 zeta with a j plus j omega over omega n square, right. Okay. So, again as you I will just do it for the pole, and the 0 is just again a mirror image. Okay. So, how does the magnitude look like? So, I am just looking at 20 log of this entire guy, right, 1 over 1 plus 2 zeta j omega this is so minus 20, the real part, this is 1 over omega by omega n square whole square plus twice zeta omega over omega n square. Again as usual, we will first look at how the asymptotic plots look like. So, here we will see, well, what happens when omega over omega n, which we defined as u earlier, is very small, right. If omega n over omega n, so this is, so this should be a log here. So, for lower frequencies, so the magnitude 20 log g of j omega is minus 20 log, it will just remain 1, this will be 0. Okay. So, well, nothing much changes here. So, for low frequencies I am still at the 0 dB line here. Okay. So, what is the other approximation? The other approximation comes when omega over omega n is much larger than 1. In that case, my magnitude just becomes minus 20 log. So, all these guys will go away, all these guys will go away. So, what just remains is just this guy, omega over omega n whole square. Okay. So, we ignore this guy, we ignore this guy. So, we will have omega over omega n whole square and then the square root. So, this square root and this 2 will cancel. So, I have something like this. Okay. So, this would be minus 40 log of omega over omega n, or minus 40 log omega minus 40 log omega n, correct. Okay. So, again at what point will these two asymptotes meet? This is again a straight line of slope now minus 40 decibels per decade and some intercept here, right. So, this can be computed because the omega 1 is already given to you, right. And when omega equal to omega n, when these two frequencies match, then this okay, sorry, this is minus 40, this will be a plus here, right, because it just jumps to the numerator, right. Okay. And then when omega equal to omega n, the magnitude goes to 0. Okay. So, I am here, I say I will just be 0 0 0 until this point. What is this point? At this point, okay, I will use a color chalk again, this guy, this still here, this is omega n, and after this point I go down at a slope of minus 40 decibels per decade, right. So, again I can just compute the errors as it is. So, what is the actual one? The actual magnitude is, okay, if I just take the square root here, it is minus 10 log of 1 minus, okay, let me again call this term as u, as I had even used earlier, 1 minus u square whole square plus 4 zeta square u square, okay, plus 10 times log of 1. This is for lower frequencies. Okay. Then Well, again for higher frequencies the error would again be the same, right. So, minus 10 log 1 minus u square whole square plus 4 zeta square u square, this is the actual value, plus now I have this 40, this is higher frequency approximation, right, 40 log of u and this guy. Okay. Now, what we see here is that it is no longer just computed by substituting a value of omega n is given to us, right. So, this comes from, so omega by substituting I just cannot get a closed form expression. So, what we see here, it is depending on of course omega n, and also for different, it will be different for different values of zeta. Okay. We will not really spend time in computing these things, but I will just show you how the plots would look like. Just before that, how would the angle look like? The phase angle phi is tan inverse of 2 zeta omega over omega n over 1 minus omega by omega n whole square. Okay. So, when omega is 0, phi is 0, when omega is omega n, phi is 90 degrees, and when omega tends to infinity, the phi, so this will be minus 90 and the phi would go to minus 180 degrees, right. Okay. So, similar thing will happen when I have this guy in the numerator, will just be this one, all other analysis will be the same, right. Okay. So, we will go back to the screen and see how these things would look like, right. Okay. So, we saw that the error was depending on zeta for a given omega n, and these are my asymptotes, right. So, this the 0 dB line till here, and then this guy somewhere here, so somewhere here. When you see that the error is maximum when zeta is very low, I am just plotting for 0, 0.1, 0.2, 0.3, 0.4, this will be 0.9, and then as this guy increases, well you see that the error kind of decreases, right. Similarly with the angle, right. So, zeta equal to 0.1, I have this angle, and zeta equal to 0.9, my phase plot looks something like this. I just plotted this directly from MATLAB. It should be straightforward to compute these guys given zeta and omega n, but just to avoid all that computational process, I am just showing you this one, right. I could not even draw this accurately on the board. Okay. So, now given all these things, how would we in general plot a Bode diagram given any general transfer function? Okay. So, the first thing is we rewrite the sinusoidal transfer function in the time constant form. We identify the corner frequencies associated with each of the transfer function. Corner frequencies were the one where the asymptotes met, for example here, well this was the corner frequency omega equal to 1. Okay. Then we draw the asymptotic magnitude plot like these two straight lines. Then what we do is we determine the errors for lower frequencies, for higher frequencies. How do we determine the error? The actual minus the approximated value, again for both lower frequencies and higher frequencies, and we draw the phase plot. Well, this is kind of straightforward. You just look at what is the formula for phi, and then you add all these phases to get the overall phase plot. Okay, let us try to do a few examples on how to plot the Bode. Okay, how to plot the Bode diagram. So, first thing is write down this transfer function as a sinusoidal transfer function or in terms of the time constants. So, I just rewrite the final expression. So, that will look like 7.5, I have j omega over 3 plus 1 over j omega, and then I have j omega 2, j omega by 2 plus 1, and then the quadratic term should look like this. j omega square by 2, j omega by 2 plus 1. Okay. So, how many terms here we have? We have the gain 7.5 and then we have this guy pole at the origin, first order terms as j omega by 2 plus 1, then we have the other first order term in the form of a 0 plus 1 and then the quadratic term j omega square by 2, j omega by 2 plus 1. Okay. So, and I will call this 7.5, the constant as g, I will call this guy g1, g2, g3 and g4. Okay. So, well, let us identify what are the corner frequencies. There is no corner frequency associated with this guy, there is no corner frequency with this guy. Well, this guy has a corner frequency of 2, then 3 and this guy has square root of 2. Okay. So, let us try to plot this individually, right. So, the first guy, the magnitude would be 20 log 7.5, right. So, it will be a straight line, right, of that appropriate magnitude. And then okay, I am not really out to scale, but I will just and then 1 over j omega would be something like this, right, with the slope of minus 20 decibel per decade. Okay. What about G2? G2 is a first order term, it is a pole. So, I will have in the axis, so it will just go straight for a while and then go down. Okay. This is like again a minus 20 decibel per decade and the corner frequency here is 2. Okay. Then for this guy j omega over 3 plus 1. So, I go till 3 and I go up at plus 20 decibel per decade, this is omega equal to 3. And then the last term, well, I do not have space left, so I will just draw it here. So, it will start at omega equal to at the 0 dB line, right. So, this is at 0 dB line for this guy, this is the 0 dB line for this guy, and after a frequency of square root of 2, it will go at minus 40 decibels per decade. Okay. So, let us see, like, so now what, how will the overall plot look like? Overall plot would be the combination of all these 1, 2, 3, 4 and 5 lines. Okay. So, well, this is okay, like this just addition of 2 lines. So, okay. So, I start with, okay, this looks close to minus 20 decibels per decade until I reach the first corner frequency. So, this line is just a combination of these two, right. And after I hit the first corner frequency, my slope decreases further. So, this will be minus 40 until I reach 2. At 2 I have a pole, so I will go further down to minus 60 and after so this is at root 2, this is 2 and at so this will be 20, this is minus 40 minus 20, this would be minus 60, this would be minus 60 minus 20 is minus 80 and then I hit a 0, right. So, that will add minus 20. So, I will have minus 80 plus 20 is minus 60 is the slope, right. So, this it looks something like this and I can actually compute what are the errors by the formula for the errors which we used. Okay. So, just to summarize, so this is how the first guy would look like, the constant. Okay. The green line would be the 1 over j omega term, right. The red line would be the first order factor which corresponds to the pole. The greenish line, I do not know what this color is called, but this would be the 0, right, the first order term which appears in the numerator, and then the purple line would just be the second order term. I add all these lines and I get a plot which actually looks like this. Okay. So, well, can we get some more information about how does the closed loop system look like? So, what I do on MATLAB is MATLAB actually shows me the stability margins. So, we will quickly see what is happening here and we will postpone the complexity of it to a little later. But what it shows me is that the closed loop system, is it stable? Well, the answer is no. Similarly here, right, if I look at how did I define the gain margin, the gain margin was I look at the point at which my phase becomes 180 and I look at how far it is from the point -1 plus j0 in the Nyquist thing. Here it translates to decibels, right. So, I am just looking at this line, and I am also looking at this line for the phase margin where I say I hit the -1 point, right, or the unit where my magnitude becomes unity. Magnitude becoming unity in the log scale would be 0 dB line, right. I do all this and it says, well, the closed loop is actually unstable. Okay, what does it mean, right? So, I have a if I just look at, so let's try drawing the root locus for this. Okay, I will just directly go to MATLAB and I will just draw it. Okay, I hope I remember the commands properly. G I will call as a transfer function, maybe the poles. So, I will have 10 and 30, and in the denominator I will have 4th order, so 1 S4, S cube, S square, S power 1 and 0. Okay, I just write the earlier transfer function in this way, and this is what I get. So, if I just look at the root locus of this guy G, okay, so if I just put my cursor here, it will tell me what is the gain, right. So, gain is 0, and if I look at, well, how the system looks like, the system here has a gain of 10, right. So, if I see, if I go till here, well, I am already in the unstable region, right. For all gains greater than this guy of 0.14 in absolute terms, I am stable. So, all gains from 0 till 0.1, and if I am at the gain of the system, which is 10, I will become unstable, right. So, that is what, at gain at 10, my poles are on the right half plane and my system becomes unstable, and that is what this guy is trying to tell us here, right, where it says that the closed loop system is actually unstable. Okay, not to worry much about this. We will keep on revisiting this several times until we understand this exactly what it means, right. So, we will kind of postpone this, where we will try to understand it. At this gain, my closed loop system is unstable. What is a closed loop system? The characteristic equation of 1 plus g times s equal to 0, okay, right. Okay. So, now we will go to this example, right, which will look a little bit familiar. If I say this is s plus 2 and s plus 1 and s minus 1. Okay. So, this is, we had plotted the Nyquist for this, right, which actually did something like this. This was 0, this was minus 2, I was encircling the point, minus 1 plus j 0 once, and then the system was stable, right. So, the open loop system is has an, this is open loop unstable, but I know that the closed loop is stable. Okay. So, how will the Bode plot look for this guy? So, I will just write this down as 2 j omega by 2 plus 1, and again j omega plus 1 and j omega minus 1, and okay, the crossover frequencies would be 1, 1 and 2, okay, from this omega is 1 over t. Okay. Now, few interesting things here. So, let us see, well, the plot of 2 would be just a straight line. Okay, let me the plot of 2 would be a straight line. The plot of j omega over 2 plus 1 would be something like this. They meet at 2 and then they do this. Okay. Now, look at these guys, right. So, 1 over j omega plus 1, 1 over j omega minus 1. So, these guys will do something interesting. So, the magnitude plot for the first guy, say I will take the stable guy first and it will just go till omega equal to 1. Sorry, this is not drawn to scale, but and it goes here, right, at minus 20 decibel per decade. Okay. Now, the second guy, again So, this is the plot for the unstable guy, this goes till here till omega equal to 1 and still be minus 20 decibel per decade. You see, because the magnitude is the same for this guy, right? So, what is the magnitude for the first guy? That is 1 over square root of omega square plus 1. The same here also, magnitude is okay. The magnitude is 1 over square root omega square plus 1 also. Okay. So, just by looking at the magnitude plot, I may not be able to say if the system is stable or not, because this will correspond to s plus 1, this also correspond to s minus 1. Right. So, what will change is the phase, right. So, this will have different phases, and I will show you the exact plots now how they look like. Right. So, this red guy is the so this red guy would be the 0 at minus 2 plus k, right, and then the green guy. So, these plots actually overlap, and this will be both the stable and the unstable pole, right, and then now look at the phase, right. So, we see that if you just remember how the first order terms look like. So, the angle started from 0, it went to minus 45 at the crossover frequency, and then here. Okay. Similarly with this guy, and then this is how the overall plot actually looks like. Okay. Again, so couple of questions which we can try to answer here. So, can just by looking at the Bode plot, can I say if it corresponds to a stable or an unstable pole? Well, just by looking at the magnitude plot, well, at least I can say that this is a pole, right, because the 0 will go up. Now, how did the magnitude behave for a term like this, the phase 1 over j omega t plus 1. I start with at omega equal to 0, I start from phi equal to 0, then omega is 1 over t, I start then I go at minus 45, and as omega tends to infinity, my phi goes to minus 90 degrees, right. So, that is happening in the green line, okay. But the blue line does something strange, right. It starts at 180 and ends up at minus 90. Okay. So, this is one thing which you can distinguish just by looking at the magnitude plus the phase plots of if it corresponds to a stable pole or not. Okay. So, how does the overall system now look like? Overall system, well, the transfer function looks something like this and this. Okay. So, what was the gain margin? Well, the closed loop system is stable, right. You could just look at 1 plus this thing being equal to 0. The closed loop system is stable, but it has a negative gain margin, right, minus 6. So, which essentially means if I draw the root locus, so I have a pole here, and a 0 here. This is plus 1, this is minus 1, this is minus 2, okay, this is 0 here. So, for some values of, so at k equal to 0, I am unstable, okay. Well, not I am not unstable, but the system is unstable. Okay, then I keep on moving until at k equal to 0.5, I reach this this point. So, my system is stable after this thing. So, the gain margin would be 20 log 0.5, right, and this will turn out to be negative or 6 decibels, right. So, minus 6 dB is the thing. And if you remember last time I said these are systems which have negative gain margin, right, even the Nyquist thing, right. So, look at how the Nyquist look like. So, this was minus 1, this was minus 2, okay. And for a system, okay, I am just really messing up this, but that is okay. For a system, when we sorted the Nyquist arguments, we say if this was A, 1 over A was the gain margin, right. So, if you increase the gain by a factor of 1 over A, the system was stable. Here what I am doing, I am decreasing it by a factor of 1 over A, right. This is 1 over 2 in the negative direction, and therefore, I have this negative gain margin minus 6.02. This I think the MATLAB will tell you directly. Of course, lots of things again will come on this while we are dealing with stability and also minimum and non-minimum phase systems. At the moment, you can just understand this from what is happening through what we learned through the Nyquist, that I really have to decrease my gain for this for k decrease my gain because open loop gain is 1, and also from the root locus it is obvious, right, that I start from an unstable system and I have to make it to a stable system, and the closed loop is stable here unlike the previous case. Yeah, that is what even the Nyquist tells us. Okay. So, okay, just before this I will just try to do one more example, right. So, okay, I will just okay. Let me say I am looking at, so far we have just been doing positive negative transfer functions, so negative gain margins. So, let us say I take a system 1 s plus 1, s plus 2 and s plus 3. Okay, this is note sheet. Okay, so g of s is 1 over s plus 1, s plus 2, s plus 3, and I could see, well, if you also plot and check, right. So, this is -1, -2, -3, and the root locus would look, this guy will go here, these two guys will meet up here and they will go here, right. So, this is k equal to 0 and this k equal to some k prime, that we'll find out. Now, okay, let us try to write this in the sinusoidal form. This is 1 over j omega plus 1, this is j omega by 2 plus 1, this is j omega by 3 plus 1, and what will come here is 6. Okay. So, I have a thing of 1 over 6 and then I have crossover frequencies as 1, 2 and 3. Okay. So, let us draw the root locus and the Nyquist both for this and check. Okay. So, I go here, I will call G1 as my transfer function. So, on the numerator I will have 1 and then the denominator polynomial would be 1 s cube plus 6 s square plus 11 s plus 6. Okay. Now, okay, perfect. So, okay, I would want to draw the root locus. Okay, so I will have root locus of G1 and let us see how it looks like. Okay, so this is almost like what I had drawn. So, you see at a gain of around 60 or slightly around, let us say roughly around a gain of 60, my system is on the verge of instability. Okay. So, that is, I would say, from 0 to 60 the system is stable, otherwise the system is unstable. Okay, let me say what the Bode says. Bode of the same guy G1. Okay. Okay, so this is how the Bode diagram looks like, and if I ask the system to show all its stability margins on the grid, then this is something nice, right. So, we will have gain margin of, this is a positive 35.6 dB, which will actually be 20 log of 60. Okay. And then similarly it will have well, it may phase margin, but it does not exist, right, it is stable for all phases. Okay, again how do we compute this? Gain margin, again we look at the phase crossover frequency at 180 degrees, right, at 180 degrees, so I am somewhere here, so this is the gain margin. The phase margin, well, I never actually touched the 0 line, so there is no question of computing the phase margin here, but this is a system which starts with a stable configuration when k equal to 0, it stays stable until k equal to 60 in absolute terms or 35.6 dB, and later on it just goes on to the verge of instability, right. There are also systems with let us say an infinite gain margin, let us say a standard second order system, say G2 is Tf, let us say this D1, this is a very simple second order system, and this is what the first example we had done when we were even doing root locus 1, 2 and 1. I guess this looks good, and let me first draw the root locus of G2. Oh, you see the root locus is exactly what we had drawn, right. So, this is for all gains k, it is stable. Okay, then you look at how the Bode of this looks like. Okay, now I go to the grid and I see how the stability margins look like, right. So, you will have a phase margin of 180 and then there is actually no, this actually never reaches well, the 180 degree, it just reaches at infinity. So, you will just have the gain margin to be infinite. You see it never reaches 180 degrees, right. So, these are systems which have infinite gain margin and a phase margin of minus 180, which is kind of very good for us, right. Okay, so okay, back to the slides. Okay, now to just before we conclude, what we will try to do is can I actually find out the error constants from the Bode plot. Okay, so let us say first we look at the position error constant. Kp, right. Okay, how was a typical transfer function like? Well, if I write it in the sinusoidal form, I have k, I have all the set of zeros, say I will call this t some number m over some poles at the origin, and I will have t1 s plus 1 and some t n s plus 1 small n, right. Okay, so and I can just write this in the sinusoidal transfer function just by substituting s with j omega, right. So, let us say n equal to 0, and this is the only case where I am interested in the position error constant, right. Okay, so, when s equal to 0, well, how will my Bode plot look like? So, my Bode plot initially will have a certain constant magnitude, right, because this guy doesn't appear, right. So, this is just 1. So, it will just be k times this or things, whichever is so all these guys at the lower frequencies are at the 0 dB line. What else changes? K, right. So, this will be something like this, and then they will go whatever, if there is a pole here and then there is a 0 and again a pole and so on, right. So, this is the minus 20 dB per decade line, and this is the first corner frequency. Okay, so, what is this magnitude? The magnitude here is, so how do we define k, the position error constant? That was limit s going to 0 g of s. Okay. Now, same thing if I say what happens when limit omega going to 0 g of j omega s? Well, that is simply k, right. This guy goes away, I just put omega equal to 0, and that is what I am left with. Now, this thing is again at omega equal to 0, right. So, 20 log of kp, and this k is essentially kp, right. So, when I write it in the time constant form. So, how do I find kp? Well, I just see where does this intersect this. So, what is this constant, and then this is actually 20 log kp. Once I know 20 log kp, I can find out what is kp. Okay. Then we look at the velocity error constant. Okay, and this is typically you are interested only in a type 1 system. Okay, so which means for lower frequencies the plot would look something like this. Right, and say the plot would look something like this, and then well, maybe after a corner frequency I just go down and do whatever. Okay, so for lower frequencies g of j omega, because the system is type 1, would look something like this. Okay, these are again for very small omegas. Okay, so 20 log of the magnitude of k over j omega. So, let us say that there is some point, so I just extend this line, right, till wherever, I do not really worry about what happens at the corner frequencies, and say what is this value at omega equal to 1? Well, at omega equal to 1, the value is 20 log times kV. So, I take this say omega equal to 1 here, I extend this line and this value would be 20 log kV. So, this is my magnitude in decibels and this is frequency. Okay. Now, well, something else also happens, right. So, I am just going down and somewhere I am intersecting the somewhere here, right, the 0 dB line. 0 dB line essentially means that the magnitude k over j omega at some say omega equal to omega 1 is 1. Let me call this frequency as omega 1, right. So, I just keep going down and this 1 in the decibels turns out to be the 0 dB, right. I am just looking at 20 log 1, that would be the 0 dB line. So, I will ask myself what is the frequency at which the magnitude of k over j omega goes to 1? Well, that turns out to be k is omega 1, right. And what is this k? This k is essentially my kV, right. All these are kVs that I can. So, what is kV? Limit s tends to 0 s times g of s, or similarly omega going to 0 j omega g of j omega. So, if I take a type 1 system, this will be 1. So, whatever remains after everything is substituted to 0 is just k, and this k is my kV, right. So, g of j omega for lower frequencies is kV, and okay. So, the frequency omega 1 at which this line intersects the 0 dB line, this omega 1 is then my velocity error constant. So, I can do it two ways. See what is the magnitude at omega equal to 1, right, and that will give some thing 20 log kV, and given 20 log kV I can always find out what is kV, or other ways I can just extend this line until I hit the 0 dB line. In absolute terms, what does this mean? 0 dB means a magnitude of k over jV at 1, and this k is essentially kV because of this guy. Okay. This is k and this is from definition of kV, this is k. Okay. So, kV can be found out by the intersection of the initial line with the 0 dB line, and the frequency at which this happens is my kV. Okay. Then this should be straightforward to visualize. We look at the acceleration error constant. Right, and you say so you will have n equal to 2 or type 2 system, right. Okay. So, here this initial thing will be minus 20 decibel per decade line, okay. And here, well, what happens for low frequencies? I am now looking at g of j omega is k, and this k a again turns out to be the acceleration error constant, right, by j omega square. How do you compute k a? Is limit s tends to 0 s square g of s, right, and then you do the j omega and whatever k is left is actually the k a. Okay. Again these are for lower frequencies. So, if I just plot, I will have a minus 40 decibel per decade line, and then maybe something else happens and so on. So, I just extend this line. Okay. So, I am interested in what 20 log Ka by j omega square. What happens to this guy at omega equal to 1? This guy at omega equal to 1 is simply 20 log Ka. Okay. So, let us say this is omega equal to 1, right, and the intersection is 20 log Ka. Other way to also compute is to see at what point of time this touches this axis. So, I am looking at magnitude of Ka by j omega a square is 1, sorry, or equivalently in decibels 20 log Ka over j omega square is 0 dB line, right. So, it is 0 dB. Magnitude of 1 in absolute terms corresponds to this guy. So, what will this tell me is that omega a, so let me just call this at omega a, right, at omega equal to omega a. So, omega a is square root of the acceleration constant. Okay. So, I just keep going this till I reach the point omega equal to, till I reach the 0 dB line, and the frequency at which this happens is the square root of the acceleration error constant. Okay. So, again these are just, this occur only for type 2 systems, Kv occurs only for type 1 system, and Kp occurs only for type 0 systems, and we know why this is true, right. So, we saw several advantages now of the Bode plots, right. Much easier to compute than the Nyquist, right. We just have to deal just by adding straight lines, right, and well, a bit of, we could visualize how the gain margin and phase margins look like, even though we will really extensively discuss that a little later. What we also knew towards the end is that given a Bode plot, I could actually compute what are the Kp, the position error constant, velocity error constant, and the acceleration error constant, right. So, that is what we learned today. So, what we will postpone the experimental determination of transfer functions via a Bode plot when we finish learning what are the minimum phase systems. I will not really even attempt to define that at the moment, but let us assume that there is something exists, or okay, just to please you I would say, well, minimum phase systems are the ones for which all the poles and zeros are to the left half plane. For example, this system was a non-minimum phase system because there is a pole on the right. So, where everything is into the left is a minimum phase system. So, just remember it that way for the moment, right. Okay. So, next class what we will do is to slowly understand the concepts of designing a controller, right, and what are the basic elements. These are, well, what they call as a proportional, a integral, and a derivative control. So, we will see how to smartly use these individual elements, when to use this. Is a proportional controller enough, or sometimes I need to add integral control? What about a derivative control? Can I actually realize a derivative control? But if I cannot realize a derivative control, what are the other methods I will do? All this will slowly try to build up the theory behind it, right. Okay, thank you.